lot of different things I need to talk about, so please forgive if it's a bit of a rambling order and so forth. Today we are starting actually 3 different labs depending on the different groups and so forth. Now, those labs will be on 2 different floors and largely in 3 different rooms. As you notice, there's only obviously one of me, so I will be moving around between them all. However, you guys are going to have to step up in terms of responsibility. If you don't know something, wait and ask or figure it out. Okay? If, for example, in the kinetics, partway through you mess up, that's a problem. Okay? Because the kinetics experiment is based on time, so you've got to keep the same time period going through and adjust for it and so on. The glove box. When the samples come out of the glove box, they're air sensitive. So don't at that point think, oh, I got to go set up the IR for my scan, okay, in the background and so forth. Have the background run and ready to go, so when you come out of the glove box, you can go immediately and take your sample there. The solid for the glove box is partially air sensitive. Because it's a solid, it's not nearly as air sensitive as the liquid. The NMR sample for the glove box will start oxidizing within minutes. Very, very quickly. I wouldn't even say minutes. I've seen them go as quickly as 30 seconds. And now, obviously, you're not going to get upstairs in 30 seconds and so forth, so we're going to do things to minimize that. But, you know, you have to be logged into the NMR and ready to go. Okay, know what it is. Don't have your sample in your hand, see your friend in the hallway, start talking to him for a minute, and then be like, oh yeah, I gotta go run this. At that point, it's too late, you're done. Okay? And you now have 3 hours plus if you're gonna try and do it. Kinetics. One person from your group has to come in on the Friday to do the last kinetics point. Sometime tomorrow, whoever is doing kinetics today has to come in and do it tomorrow. You have to work that out. The person oversleep's not a big deal because they can do it at any point, but if they just forget about it, your data analysis is, you don't have that value, you're done. Okay? So, I know we're all college students, we're all adults and so forth, and me personally, I tend to put a lot of responsibility on you all to be adults and do the things you need to do and stuff, and then I forget when I was a student, that's not how I was. But this is one of those cases where, you know, 4 different experiments going on at the same time. I'm gonna be all over the place. If you say, what is this, and hold something up, I have no idea what that is. Okay, I didn't watch you do that. Okay, so we'll have to go through the steps and so forth. So please, please plan accordingly, talk with your group. When you have time during the experiment, figure out what you're going to do next, those types of things. Each of the experiments have little different things associated with it to watch out for. I'm going to talk about them to a certain amount today, but with that being said, you know, if you have questions, ask. And so forth. There we go. So, few general announcements. With short reports, I ask that you turn in the short report. It is a printed copy and an electronic copy on Blackboard. If you go to Blackboard, there's a column that says short report and so forth. For the experiment, you just attach your file there. Please do that by the end of the day if you haven't. So you can think of labs when they're due. You can hand in the printed copies and so forth, but I won't count off or anything if you don't submit the electronic at the beginning of lab. But please have it done by the end of the day, so that way I can go ahead and grade them and so on. I know people think it's stupid to have me ask you to hand both in, but it does make a difference, especially in formatting and these types of things. You will be graded on formatting and so forth. So actually, to be honest, today we've already had a case where one version is screwed up and the other one looks fine. So I'll play them against each other to some extent. But please make sure that you submit both the printed version and the electronic version. Also, when you hand in the short reports, that's when we should be handing in our notebook pages if I don't collect them during lab. So for the metal ACAC experiment, let's hand in the notebook pages today. I don't care if they are the carbon copies or the white copies, as long as I can read it. That's really the whole main thing. Just so that I can actually read what's there and so on. The formal report for the ACAC is going to be due next Thursday. I am going to grade your post-lab questions today and tomorrow morning, and I'll put them outside my door for you to pick up. But I know many of you, I almost don't want to say this, but I know many of you are not here on Friday, and that's perfectly fine. That's not the point. I will email you a scan of your report as well. So that way, if you choose, you can start working on it over the weekend. Please plan accordingly and put the time in on it. I wish there was something magical I could say to get you to believe me, but the formal reports is about formatting, writing, nitpicky things. At the end of the semester, well, how you guys will, numerous times in reviews, people say Dr. Steve is very nitpicky about grading the reports. Yes, I am. Absolutely. If you put 2 periods where there's supposed to be 1 period, you can lose points for that. Okay. Anything. Okay. These are formal reports, so treat them as if I'm your boss, and I've asked you to write or report to go to the president of the company, and so forth. Okay. You're not going to make mistakes in those types of things. So please realize this. It's not really an hour assignment. On Blackboard, there is helpful hints for the formal this time, mostly topics that should be included, things along those lines, as well as a very lengthy file on writing. So please look them over to make sure. The reason why I want you guys to get your post-lab back is because of the fact that many of the answers there you're going to be including in your formal report. They won't be graded for correctness, if you will, in the formal report, but you'll have to include them. So for example, the major points like the IR shift, hopefully we all saw an IR shift, you're going to have to discuss that in your report. So that's the idea there. Questions about that stuff? Everyone doing okay today? Thursday? 3rd week of classes? Things are starting to get busy and so forth. Okay. Another announcement. For the 2 people that are here that are doing the glove box outside of class, usually you guys, next Tuesday morning, 8:30 still works? Yeah. Okay. So talk to me, I'll give you a little heads up about that. Today we'll be good with that. Topics. I went ahead and made the topic assignments for the pre-labs. They're just short little questions about what the topic is. Today, at the end of the day, I want to finalize that list, and then I want to talk to you about what your topic is. Okay, just to kind of narrow it down what I'm looking for, so you kind of have an idea of what it is. So for example, one of them is, why does an octahedral show a 3-2 arrangement? That really could be a million different things and so forth. But I'll just talk to you and tell you specifically what type of things I'm looking for there in each of the different topics. So that way you know a bit more than my short little title of what everything is. But I should hopefully have a chance to catch people today to talk to you about what those topics are to some extent. We had an odd person in class. That sounds weird. An odd number of people in class. So one group has 3, so that way no one has to do it on their own. There you go. Okay. That brings us to the experiments today. Everyone read through their experiments, understand the basic gist of what's going on. Okay. Starting with the glove box experiment. Who's doing the glove box today? Okay. What you're going to be doing is you're going to be making a copper compound. And this pre-lab I'm not going to do every week for it. I actually had the bright idea to record it because Kelly's not here for one. But I'll make that available for people so you can review it before each week if you want. But you know, just because you're not doing glove box today, don't blow it off. You know, and think, oh, I'm not going to worry about that because we're not going to do this every week. In the glove box, you're going to be making a copper compound, and that copper compound is actually a copper 1 compound. Now, the reason why we're going to do it in the glove box is 2 reasons. Number 1, it gets you experience of working inside the glove box. How many people have worked inside the glove box here? We're all like sitting together. Okay, that corner has worked inside the glove box. Everyone else hasn't. That's normal. It's actually more than I expected. When I was in undergrad, I did work in a glove box, but that was because the physics department worked with glasses that were air sensitive, and I helped them out somewhat. So I did a little bit, but in grad school, almost all of my work was inside of a glove box. I couldn't even guess how many hours I spent inside of glove boxes measuring things out. We worked with rare earths, so the lanthanides in particular I worked with, and most of them are air sensitive. Several of them are air sensitive to the point to where if they're exposed to air, they kind of catch on fire. So you can't really do it outside the glove box. So we did a lot of that type of work. We set garbage cans on fire all the time. It's just what happens. We would have powder, and it would get on the paper towels. You wouldn't think much of because you'd wipe it off and nothing would happen. Then you'd bring the paper towel outside the glove box and put it in the trash can. It would hit the air and it would start a fire, and of course the paper towel burns well. So we just kept fire extinguishers next to the garbage disposals. It was just a thing. So the glove box keeps air away from it. In this case, the air we're concerned about is oxygen because the copper compound will oxidize to a copper 2. What do we know about copper 2? Do we know anything about copper 2? Well, it's +2. Not that much, right? What?
Blue.
It's blue. That's what I was looking for, actually. That's really about all I know about copper 2. It's blue. So when you see copper in the blue color, it's very, very characteristic. So when we're looking at our samples, if, say, we bring it upstairs to put it in the NMR, we go to put it in the NMR and our solution is blue, that's not a great sign. If we go to take the IR and it's starting to turn blue, we may want to, hurry up a little bit. There's really no huge trick to it. In an ideal world, we would have a atmosphere-controlled IR that we could then have argon or something on so that oxygen wouldn't get to it. We don't have that, so we just go really fast. And then we deal with it, if it is. The other thing about copper 2 is if we count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it's the 11th one over. So what would the D count be for copper 2+? D9.
Isn't an exception?
What?
Isn't an exception for us? No, never mind. I'm thinking of something else.
Okay.
Don't mind me.
Okay. I believe it's going to be D9. Either way, it's going to be an odd number. I think I know what you're talking about. I think you're right. In this case, though, it does actually go to D9. And the problem with that is because it's an odd number, the NMR is not happy about it. So if we start getting blue in our structure, it messes up with the IR. Okay? If it stays nice and clean, we can get a nice IR, not IR, NMR. Okay, it messes up with the NMR. So as long as it doesn't turn blue, then we should get a nice NMR for us to do our analysis of. If it changes to the full 2+, it doesn't look very good. So we'll be there. When we're working in the glove box itself, there's a lot of safety things you have to know. The first one is don't melt the gloves and don't poke holes in the gloves. If you think to yourself, oh, you know, I may poke a hole in this glove. What I'm doing may poke a hole in this glove. Anything along those lines, stop. Okay. Gloves are very expensive. We don't want to replace them. So an example of this is if you're taking pipettes into the glove box, and we'll talk about this downstairs as well, you're always going to take the point of the pipettes and point them away from the gloves. So that when you grab it with your hand, you're grabbing the dull end and not the point. Because if the point is out and you put your hand like that, you could poke a hole in the glove and then we'll all cry. And you're going to be the one to tell Dr. Edwards he needs to change the gloves, and he'll get mad, and it's a whole thing. Okay? So we just will not do that. If you do, it's not the end of the world by any means. People have done it many times before, but we're going to avoid it at all costs. Melting your gloves is actually much worse because your hands are in there on the plastic, and then you got melted plastic in your hands, and you'll get a burn. Okay, so just be aware of that. The hot plate will be hot, and you can't like put your hand close to it to see if it's hot. Okay, because the glove will block it. Like I do that in here all the time with heating mantles for organic. I turn it on and I put my hand close just to see if it's warming up and so forth. That's not something you can do in the glove box. And then you're going to be working inside of gloves, which is going to make everything feel really weird. Okay, if you've never done it before. This is actually a great experiment. It is a pain in the butt for me to do because of switching people around and the number of people and the time and so forth. We still do it though because it's really, really important for you guys to get a little bit of exposure there. After our synthesis and recrystallization inside the glove box, we are going to collect our product with suction filtration. We are going to use suction from a pump to do this, but we need to make sure that the valve for this is closed when we're done. Not like I think it's closed, like triple check it's closed. We messed this up one time, and students came running in a panic because the gloves had been sucked inside, and they didn't know what to do. Right? And they said, oh, I screwed up, and we fixed it. It's really one of the easier fixes, but it's thankfully they were smart enough to recognize something was wrong, which would really be hard to notice when you look at the glove box. But anyway, triple check that is turned off. And I will absolutely do my best to remind you of that, but you guys have to help me remember that as well, because I have personally messed that up. And then finally, for the IR and NMR, just make sure that you're prepped and ready to go when we're coming out. You can have it in the antechamber, come upstairs, prep everything, come back down, take it out of the antechamber, and go straight to your measurements. NMR and IR, today, the glove box group has priority over everyone in the building. Okay, so I've signed up for it and that stuff. We'll kick off. If someone else is running an NMR, we'll kick them off so that we can run the NMR, because we really don't have an option. The other thing about the glove box setup is I have the instructions printed for the glove box right here. We're going to tape those up on the glove box, and you literally just follow along with what it says. We will break them up into thirds roughly. The first person is going to pour it in and then do a little bit of measurements. Second person does the recrystallization for the most part, and then third person does the isolation and putting it into the sample. All in all, this takes several hours to get through. So be aware of that. Each person's not in there several hours, but you'll get the gist of what we actually do. So the glove box really is to protect the compound from oxygen. We can do that up here using slink lines. We haven't talked about Schlenk lines yet. There are two of them set up in the hoods over here, in the middle hoods. Across the top, you see the glass lines there. They're used to control the atmospheres. Every hood in here, except one, will have a Schlenk line in it a little bit later in the term, and we all get to use them and get used to using them to some extent. There are pros and cons of the Schlenk versus the glove box. It really depends on what you want to do, which one is better. This one actually works better in a glove box because we want to do a recrystallization. So we're going to heat it and do suction filtration and so forth inside the glove box. But you could do all of it inside the Schlenk line as well. So that's the glove box. Any particular questions about that one? Okay, the next one is the kinetics. When you're doing the kinetics, you need to collect at least 2.5 hours worth of actual data on Thursday, and then also the Friday one, because we need to get enough data points so we have a good trend to see what is actually occurring in the kinetics. In the experiment itself, what we're doing is we're taking this compound here and we're substituting water in for the Cl. That's going to cause a color change. That color change is going to be measured through the UV vis down in the laser lab. So we're going to have our samples in here. They're going to be kept in this water bath, which actually does a really good job maintaining the temperature at 80 degrees, or sorry, 60 degrees, not 80, 60 degrees. And then you're going to take your sample from here, put it in the cuvette, go down and measure it. Many weeks we're going to have two groups doing kinetics, and they're going to have to alternate between the two. So you're going to put your compound into water, add the acid to see if the acid basically catalyzes your reaction, and then watch the kinetics of the substitution. And we're going to watch it over several hours so that we can map out exactly what's going on. Now, in terms of the kinetics, there's a few different options. There's the SN1 replacement, SN2, or what I've got called is the special, which is basically the acid catalyzed version of it. In SN1, what would happen in that case is this chlorine would leave, leaving basically a vacancy around your central cobalt atom, and then the water would come into it. In the SN2, what would happen is the water would come in first to create basically a 7-coordinated cobalt, and then the chlorine would leave. So that's the fundamental difference there. And then this acid version is basically a catalyzed version of the SN1, where the acid would help facilitate that intermediate, where the cobalt leaves. So if it is acid catalyzed, what would we see as a fundamental difference between the kinetics?
The rate constant would change as the concentration of acid changes.
Exactly right. The rate constant is going to be dependent on the concentration. So in this experiment, what we're doing is we're going to be running two different dissolutions, and those are going to be at different concentrations of acid. So one of them is 0.1, and one of them is 0.3 nitric acid. So we're going to have two of them there, and you're going to be basically recording the data and looking at what happens as a function of time. So if that is the concentration of this decreasing there, then do we see a significant change in slope as a function of the acid? When we do the derivation of this, you can very quickly see that it's a direct relationship between the acid concentration and the rate. So between these two, you should see the difference in the concentration. So this should either be 1/3 or 3 times as you go through it. if, for example, you see a difference here, and the difference is 90%, then that's probably not a case. That's probably just measurement issues. So not only are we looking to see if there is a change there, that change should be able to be explained by the concentration of the acid. And that's something that's tripped up students a lot in the past. They see one slope as maybe a slope of 1 and the other is 1.2. And they say, oh, there has to be acid catalyzed because of this. Not necessarily. Okay? Or what you're looking for, and what students may see in the past, is 1 and 3, or 1 and 0.3, or something along those lines as we're going through it. So we're going to look at it as a function of the acid, and then we'll see the change that occurs there. Physically, what we're going to do is you're going to put your nitric acid inside your volumetric. Go ahead and fill it all the way to the 100 directly. Don't worry about the little volume change that's associated with putting the solid in, because it should be the same, because you're adding the same amount of solid to both of them. And we want to heat the nitric acid first. So we're going to put the nitric acid into the volumetric, put it in the water bath, and let it heat for 15 minutes so that it can get to 60 degrees. Then you're going to put your solid in, cap it, shake it really well. Once the solid is dissolved, let's say 95% or better, draw your sample out and go do your measurement, and that will be time 0. And then after that, we're going to be, I forget exactly how often you take your sample. Is it 20 minutes?
15
to 20.
15, okay. So every 15 minutes after that, you're going to be taking another data point. Now, you have 2 of them. So as a group, you have to figure it out how you're going to collect them both, because you need to do the 0.1 and the 0.3, and then 15 minutes later, do the 0.1 and the 0.3 again. Keep them in the same order so that you're not shuffling your times around and so forth, and always use the same point to define your time. So if your time is defined by when you pull your sample out of the water bath sample, use that as the time. If it's when you start your sample scan down the hall, use that as the time, but always stay consistent. Okay? If for some case you end up with a 17 minutes split, then record that as 17 minutes. Don't record it as 15 minutes. What will happen is, instead of having your points nicely spaced out exactly the same, one of them would just be a little longer. It'd still fall on the same path, but it would be further down your line or something. Okay? As long as you keep the sample time the same, or the sample time the same point, then you should be okay going through it. And that's really something students have messed up with in the past. So you shake it up to dissolve your stuff, and then once it's dissolved, that's your sample 0. Don't spill the starting material or waste the starting material or anything. This is homemade stuff. It's not exactly the easiest stuff to make. It takes a while to do, so if you spill the vial of sample material, you're going to make another vial. Okay. Just straightforward, simple as that. Collecting your data, you're going to collect at 532 nanometers every time. Use your cursor to find exactly 532. Don't approximate that. We need to be exactly 532 every time. Don't always take the highest point on your spectra. Don't just 532. I know that sounds weird, but last year students decided somehow to take the highest point on their curve, and that just kept shifting, and then the data didn't make any sense. Okay. 532. Okay. Clean your cuvette, rinse it out between runs, probably not a big deal. Don't forget about your Friday one. down there on, how many people have used the UV Viz before down the hall? Anyone?
I used it on Tuesday.
Oh, see, there you go.
Yeah.
Okay. Okay, one of the things is we're going to be doing the two beam setup. So make sure that you have water in the reference beam. And then always put the cuvette in the same way. I know this sounds silly, but students make this mistake. I make this mistake all the time. Okay? You need to be shooting through the clear part of the cuvettes. Okay? If all of a sudden you switch the frosted part, obviously your numbers are going to drop significantly. Right? So keep that in mind and make sure you're shooting through the same one. The water reference, I would recommend just to leave in there all the time for all groups. Okay? Don't try and switch that out or anything. But you may end up with two different cuvettes for, like one for the 0.1 and one for the 0.3. That's fine, just don't mix them up. And then take them out and then put them in and so forth. So I'm pretty much going to leave it to you guys on the UV Viz because I'm going to be downstairs most of the day. I'll be up and down to kind of help out as I can, but be aware that I can't. Some things they can do in the glove box without me, but it's relatively limited. So plan accordingly. Okay, so there you go. Questions about the kinetics? I think I just got one group doing kinetics today. Who's doing kinetics? You guys? Okay. Here is a data sheet for you to get started with.
Cool.
Just to kind of make sure we're all on the same page. Up here. Okay, so that is the first two experiments. The third experiment is the tungsten oxide. And for this one, I don't have nearly as much of an explanation. But what we're doing with the tungsten oxide is we're taking tungsten oxide and we're going to be reducing it by creating hydrogen inside of the material itself. So tungsten oxide is going to go into hydrochloric acid, and then we're going to add zinc to it. When hydrochloric acid reacts with zinc, that's going to create hydrogen gas. That hydrogen gas is then going to intercalate inside of the tungsten oxide. What that means is in tungsten oxide, we have layers. They're not as separated as graphite, but you can think of it as a layered structure. And the hydrogen is going to go inside those layers, and it's going to cause a structural change inside of it. We can think of it primarily as just shifting the layers apart to make room for it, and that's what an intercalation really is where things go inside of your various layers, and traditionally intercalations just kind of split your layers apart to make room for it and so forth. Perovskites is a very, very common material for intercalation. And there's literally thousands and thousands of different intercalations of these perovskites. So this is going to go in there, and we're going to see two things. One, as the layers split apart, you're going to get a shifting of your octahedral. So you do get a little bit of a change in terms of that. The other thing that's going to occur is a reduction of the tungsten. So the tungsten starts out as +6. You're going to see a partial reduction of that. It's not all going to become +5 by any means, but a little bit of it is going to become +5. What that does, when you have a reduction, you're adding electrons, right? Reduction, Leo the lion, whatever it is. I teach it in my class, I should remember that. You add electrons to it. So in tungsten oxide, you guys have just started learning about band structures, right?
Yeah.
Just very beginning of this type of thing. So we're not really going to go into it. Okay, here's my band structure.
Beautiful.
They look like that, by the way. That's exactly the band structure. We always call them spaghetti plots when we were in school. That's actually what people do who do it for a real living. Like we used to do these in publish them and stuff. That's what they're called, spaghetti plots. They look like spaghetti. So in tungsten oxide, you have basically your Fermi level, or the number of electrons goes right up to the gap. And this gap here is what causes it to be an insulator. But once you start putting electrons into it, where are those electrons going to go? This band down here is completely filled. So the only place for those electrons to go is actually into your conductive band up here. So you start populating above your gap. Once you start populating above your gap in your conductive band, that is going to change the properties of it to a metal, or somewhat of a metal. And you're going to start seeing your conductivity occur there. The other thing that's going to occur is we no longer have this gap for the electrons to jump across back and forth. And then release energy. So the color is going to change. So when we think of molecular orbitals, we know that, for example, copper 2+ is blue because of the molecular orbitals and the electrons moving up and down, right? We've all talked about this in our various classes. Those electrons, the same thing here. The electrons move, and that causes colors to occur. Once we start populating up here, you're going to change the colors associated with that. This is actually one reason why metals are generally shiny, okay, because of the fact that you're actually populating your conductive band there. And insulators tend to have all different types of colors associated with it on the first approximation when you write. So that's the idea. So as we do this, we're going to be causing an electronic change to our tungsten oxide. We're going to see that in terms of the color and in terms of the conductivity. Ideally, we would also see it in terms of the X-ray diffraction, but our diffractometer is down right now, so we're not going to worry about that part. To measure the color, you're just going to look at it. Okay, it's highly technical there. It starts out yellow, by the way. Tungsten oxide in its pure form is yellow, and then the color is going to change. You can actually get a whole variety of different colors. On your sheet, it's got blues, purples, reds, orange, yellows, golds, as you go through the system. The other thing we're going to do is the conductivity. And to measure the conductivity, we've got these little setups here. And I'll help the groups out when it comes time for it. But you've got a plastic spacer, and then you've got 2 screws that are brass, and they're conductive. So what you do is you open it up, or you put 1 screw in one side, fill it with some of your material, put the other one in, and then tighten them as much as you can. That then gives you a conductive end that you can think of as wires that are then pressed onto your sample. And then we're going to measure the resistivity across the brass screws there. An insulator should have a very high resistivity. A conductor of some sort should be less. And we'll see whether or not we can approximate the amount of zinc used back to these types of readings. So if we use a certain amount of zinc, you always get the same color. If you use a certain amount of zinc, you always get the same relative conductivity and so forth. So for that one, experimentally, it's really not that big of a deal. You're just putting the stuff together. A lot of bubbles are going to come off. Wait until all the bubbles are done before you finish up with that, and then you go on. And then I'll talk to those groups a little bit later on, because I'm getting tired of talking. Questions there? Okay, well, you can be happy. That's the pre-lab for the next month. So if you break it into like 4 segments, it's not so bad. Okay. Make sure you're wearing your goggles. Make sure you're wearing gloves as you're doing the various experiments, especially with the tungsten oxide. It even makes a point to point that out there. tungsten oxide. Oh, sorry, I keep pointing. Kinetics is here. Tungsten oxide is back there. Then the glove box is here for the initial thing, and then we'll be downstairs for the rest of it. So I guess with that, let's go ahead and break up and get started. I'm going to work with the glove box first, but I'll be up here for the next while.
Yeah, I can do that. Where do you need us to turn these?
Folders
Alright, do you want
over
to
there.